E-bikes are one of the fastest growing categories in the cycling industry. They help riders go faster, further and longer without tiring yourself. Thus, I wanted to get one and try it. So I started to search for e-bikes on the internet, but sadly most of them are too expensive for me. But finally, I found e-bike kits relatively cheap, so I ordered one from AliExpress that cost me around $190. After the assembly and testing the controller that comes with the kit, I noticed that it can be ameliorated. And since I've been working on BLDC motor controller for my graduation project for a long time, I decided to improve its features and particularly the pedal assist system. So this video will go through all the work I did to improve the pedal assist. Firstly, let's look at the pedal assist and how it works. Then I will show you how I made a really cool pedal assist system, very different than what you usually get in most e-bikes on the market. Most e-bikes have a pedal assist feature built in that lets you activate the motor by pedaling instead of using the throttle. You just start pedaling and the motor will power up automatically. To operate, the controller needs to sense that you are pedaling by using a cadence sensor or torque sensor. A torque sensor needs to measure the force that the rider is applying to the pedals, but cadence sensor is measuring the speed of your pedal. In this video we are interested only in cadence sensor. Most e-bikes on the market use that sensor like a switch. When you start pedaling you will get full power up to the level of assistance you have set. It's usually a percentage of full power, like 10% for level 1, 20% for level 2 and so on. People like this kind of sensor because you don't have to work hard, so you will ride to your destination and arrive less sweaty. The motor can make up the difference between what your legs are putting out and what is required for a given hill. The cadence sensor allows you to achieve this behavior quite nicely. It provides independent control of motor power and your pedal effort like a throttle, but without needing to constantly hold the throttle position. But the problem with this sensor is that you cannot control well the linear speed of the motor, because it has a fixed level of speed to attain. For example, if you ride with someone, you will notice that when you pedal, you catch him really quickly, so you stop pedaling, or you put a lot of distance on him and stop pedaling. That's why I decided to make a better pedal assist system based on the cadence sensor. This new system will scale well to your input, unlike other controllers. Also, you can adjust some parameter to feel that the e-bike is responding to your pedaling effort just like it would with the torque sensor, based only on the pedal cadence. So basically my controller will sense how fast you pedal and estimate the power needed to be delivered to the motor in order to maintain that speed. The cadence sensor comes with a magnet ring attached to the crank arm. When those magnets passes the sensor, it generates a signal that pulses up and down as the pedal is rotating. I then connected my oscilloscope to see those signals. When I rotate faster, the timing between every pulse decreases. My plan is to connect the controller to the cadence sensor to read the signal and measure the time between every pulse. Then I calculate how much power is needed to the motor. This section is divided in two parts. The first one is measuring the speed of the pedal using the microcontroller timers. Second part is implementing the equation that will calculate the duty cycle needed to achieve that speed. In my BLDC controller I'm using STM32F411. That microcontroller has a feature called input capture mode. Input capture is to find the time span between two rising or falling transitions in an external signal. When the desired transition is detected, the timer hardware automatically captures this time instant by copying the value of the free run counter to the compare and capture register. At the same time, the timer generates an interrupt. We can calculate the pulse width, the period, and the duty cycle of the input waveform by using 2 or 3 consecutive captures. Each input channel in the microcontroller has a configurable digital filter and an edge detector. For the simplicity of the video, I will only show how to detect rising edges, and in future video I will cover up how to detect both falling and rising edges to know if is it forward pedaling or backward pedaling. I have chosen a frequency of 1.5 kHz and an overflow of 0.7 seconds. I have set the capture compare interrupt enable, update interrupt enable, input capture filter, capture enable, and I enabled the counter. Also I have set the interrupt. Now we need to find the gear ratio between the cranks and the freewheel. In my example I used the 5th coke because I have some spacing issues. The ratio is 2.5, that means when the cranks makes 1 revolution, the wheel will make 2.5 revolution. Thus we can calculate the rate of pedaling to estimate the speed and apply the voltage needed to the motor. Well, there is two ways of doing that. One will be measuring the actual speed of the motor and try to increase it to match the rate of pedaling, which is more accurate. The other solution is to estimate the voltage required by the motor using the voltage constant. I choose the latter because the inaccuracy of this method will give more natural and better riding experience, and you will know later why. The first equation is the theoretical no-load speed, and the second one is the nominal speed, where we take into consideration the voltage drop and the losses. In our application we will replace that speed by the rate of pedaling, multiplied by the gear ratio and estimate the voltage. But before that we need to determine the voltage constant kV. I couldn't find any document that indicates the motor parameter, so I had to do some experiment to identify it. You can check the link in the description for more details of how to measure the voltage constant. After few tests and a bit of calculation I got it. With this constant I can estimate the speed of the motor at a given voltage. After a bit of calculation I got this equation multiplied by some gain that take the speed of the pedals and give us the duty cycle of the PWM to apply the desired voltage to the motor. In this equation I didn't on purpose calculate the voltage drop of the resistance, which will result giving us wrong estimation of the speed during significant voltage drop of the resistance because of large current flowing. But after few experiments I like it that way, because you will feel that you apply a bit of pressure when pedaling that makes the ride feel more natural, and during hills where large current is flowing you can shift to a lower gear and the motor will spin ahead of your rate of pedaling, therefore you can climb the hill without any effort. After running the code I captured the data and plotted in MATLAB, and I got this graph where the figure on the left is the pedal timer and the figure on the right is the output of our equation. It's very noisy as you can see. No way it can be fun to ride with this kind of output signal. Therefore, the solution is to use digital filters, because filters could be used to smooth the signal, and this can be useful in our application. There are two broad classes of digital filters, FIR filter and IIR filter. The equations for both filters are shown here. The X are the input signal amplitude, the A and B are the widths, and the Y are the output of the filter. Both those filters have their pros and cons. FIR filters are easy to implement. An IIR filter has an advantage that for a similar filter roll-off as a FIR, a lower order or number of terms can be used. This means that less computation are needed to achieve the same result, making the IIR filter faster computationally. In my application I will use IIR filter. You can find out more about digital filters in the link listed in the description. Now I want to identify the weights A and B. Fortunately MATLAB can do all the hard work and calculate for us those values. The only thing I need to do is to provide the filter type, the order and the cutoff frequency. After trial and error I landed on second order Butterworth filter, and this will be the equation of the filter. Now after implementing the filters, the result looks so much better. Even if I apply a really bad input, as you can see it will correct, thus making the motor run very smoothly. This is side-by-side comparison between two pedal assist systems. On the left side, the motor is connected to the Chinese controller that comes with the kit, and on the right side, the motor is connected to my custom controller. As can be seen on the left side, there is no control over the linear speed. No matter how fast or slow you pedal, the motor will always spin extremely fast. Whereas on the right side, where we have implemented our new system, we can control the speed of the motor by the rate of pedaling. The controller senses how fast you pedal and estimates the power needed to be delivered to the motor, therefore giving a much better riding experience. After the test ride, I can say that the motor runs very smoothly and it gives you such a nice feeling to ride. At the 5th gear, the e-bike feels like it's responding to your pedaling effort based only on the pedal cadence, even at low speed. Also, we can adjust the gain that we have implemented in our equation before to have different ride feelings. At low gain, you feel that you are doing slight effort, whereas at higher gain, you feel that you put very little effort when accelerating, but after a brief period of time, the motor will catch up, and its speed will become slightly ahead of your rate of pedaling. If you want to ride without any effort, you can shift to a lower gear, and motor speed will be always ahead of your rate of pedaling. Also, the e-bike still scales well to your input. The faster you spin, the faster the motor will run. At the 5th gear, I feel like I am applying some pressure and the speed of the motor will fall off due to the additional voltage drop incurred at higher current as the torque increased. So I shifted to a lower gear and there was no effort at all when pedaling. I'm just touching the pedals. The motor will do all the hard work for you because it's spinning faster. To summarize, this system scales well to your input. You can control motor speed by the rate of pedaling. Adjusting the pedal assist gain will give you different ride feelings, and shifting to a lower gear will give you more effortless ride, because the motor will spin faster than your rate of pedaling, but you still have control over the linear speed. Anyway, thanks for watching, and if you enjoyed this video, be sure to hit that like button and subscribe. Also, if you have a question or suggestion or any new idea to improve the e-bike, make sure to drop a comment below.